Hey guys, it's Brian here with another episode on aerospace engineering. Today I wanted to talk a bit about thrust, um, the mass flow rate, and kind of the idea that the rocket mass changes as the fuel and oxidizer inside of it are burned in order to generate that thrust. So without further ado, let's get started. To begin, we're going to understand that the thrust is actually just a force. And we know from Newton's laws that generally force equals the mass of an object times the acceleration of that object. And so that's what I've written right here on the whiteboard. And as you can see, I wrote force equals mass times acceleration. In green, I put the units just to be thorough. So here's me breaking it down. That's just mass times acceleration. That's going to give you the units kilograms times meters per second squared. In other words, mass times acceleration. And then we know that the kilograms times meters per second squared is known as the famous unit Newton, named after the genius of the 1600s, Isaac Newton. So aside from force equals mass times acceleration, we're also going to have to be comfortable with another concept. This concept is known as conservation of momentum. It's actually a physical law. And what it states is that momentum is conserved. This can be thought about by placing yourself on a skateboard and throwing a brick in one direction. You will in turn be moved in the other direction after you throw that brick, meaning that the momentum was transferred from the brick to you on the skateboard. So here I've made a little drawing of the skateboard guy throwing the brick, and then these arrows below him and the brick are just showing the velocities of the direction of these objects. So as you can see, as he throws the brick to the left, he moves to the right as a consequence. This is proof of the law of conservation of momentum. Okay, so now a rocket kind of operates on the same principle as the whole brick and skateboard idea, except now the brick is going to be the exhaust velocity from the diverging nozzle that you see at the bottom of a rocket when it's sitting at the launch pad. And the skateboarder and the skateboard are going to be the rest of the rocket. So let's take a look at a diagram to get a better idea of what I'm talking about. So what we're looking at here is the combustion chamber, the throat, and the diverging nozzle. And then as you can see, the red arrows are the exhaust velocity of the gases that are being combusted in the combustion chamber. Now, this just happens because the pressure inside the combustion chamber is greater than the ambient pressure outside of the rocket nozzle. And so things just naturally flow from greater pressure to lesser pressure. Now, because the exhaust velocities of these combusted gases is very high, it actually provides enough momentum out the back to kind of trigger an opposite reaction, which actually lifts the rocket off the ground against the force of gravity or against the drag of the atmosphere, or it just works to accelerate the rocket in the vacuum of space. So this is where it gets a little tricky. So as you might have guessed, as the fuel and the oxidizer are depleted, the total mass of the rocket decreases. This is a problem because it means that the mass is just not going to stay constant through the rocket's entire flight path. So as these fuel and oxidizers are used up and they react with each other and they're spit out the back, we're going to have a changing mass on the rocket. Sorry, the rocket is going to have a changing mass. So again, here I show the equation, momentum equals mass times velocity. And just for the sake of being thorough, I've again included the units. Now, unlike the mass times acceleration where you had kilograms times meters per second squared, which is mass times acceleration, we just have kilograms times meters per second. They're very similar, however, there is no special name for this unit. It's just simply kilograms times meters per second. So just to be clear, in that previous equation, P is the momentum on the mass that is moving with a scalar velocity. Now we're going to derive the average thrust or force on the whole system. Okay, so here I've written down the average force on the system. This top part here describes a mass that is moving with changing velocity, but then also the second part where it says V times dm over dt, that is talking about part of the system staying at a constant velocity while it changes mass. And so by convention, I just decided to write that dv over dt is equal to exit velocity, exhaust velocity dot, and dm over dt is just called m dot. So v dot is going to express the changing velocity part of the system, and m dot is going to represent the changing mass over time. So astonishingly enough, if we take those previous definitions of v dot and m dot and put them into this equation, we end up getting F equals, and that's going to be m dot v exhaust plus v exhaust dot m. And so you see the dots are kind of switched around there, and that is pretty cool, I think. So that's just an easier way to write it. Okay, so now I need to be clear about something. So in that previous equation that we wrote down, the left side of the equation, which is m dot times the exhaust velocity, that describes the momentum of the rocket with a changing mass and a constant exhaust velocity. An easy way to remember this is that the exhaust velocity will be constant because it is a result of the chemicals that are being mixed in the combustion chamber in order to produce those exhaust gases. Now this right part here, the V dot M, is a little bit more complicated, and we're going to go into it right now. Okay, so another thing we're going to talk about in a later video is going to be the velocity of supersonic and subsonic fluids through diverging and converging nozzles. But for right now, just take my word for it that supersonic velocity fluids will always be accelerating even faster through diverging nozzles. And that is the reason why V dot, which is defined as acceleration, is part of the thrust equation. So now that we're talking about exhaust gases in the diverging nozzle, we can use another definition of force that we know that involves pressure and area. And that's just that a force is equal to the product of pressure applied to an area. And I'll write this down right now. Okay, so simple enough. This thing is really just force in terms of pressure and area. Not really a big deal at all. And so where this comes into play is when I mentioned the pressure in the combustion chamber becomes greater, and as those hot exhaust gases begin to push on the walls, the inside walls of the combustion chamber, they are going to want to leave to the volume of ambient pressure which is outside of the rocket engine, which is the whole reason the exhaust velocity even exists. So what this means is that there is a pressure difference between the inside of the rocket nozzle and the outside of the rocket nozzle. And this can be quantified as, let's say, P sub E minus P sub 0, where P sub E is the pressure of the exhaust just inside the rocket nozzle, and P sub 0 is going to be the pressure outside of the nozzle. And so we're also going to, we talked about area, so F equals PA. So now for the nozzle, we're going to talk about the exit surface area of the nozzle, and that's going to be our A exhaust. And so the equation is as such. Okay, so as you can see, I rewrote the first equation, force equals pressure times area. Now that indicates that the force on the inside of the nozzle equals the difference in pressure between the pressure on the inside of the nozzle and the pressure on the outside of the nozzle multiplied by the exit surface area of that nozzle, which is represented by the symbol A sub E. Okay, so now remember we were talking about the section of the thrust equation that was exhaust velocity dot times m. And so I'll just write the thrust equation again, which was this. So F thrust equals, and then so we discussed that m dot is pretty intuitive. The mass is changing with a constant exhaust velocity, and then we have to factor in, so remember we said V dot m. And so this part of the equation right here, that actually equals this right here. So our thrust equation by substitution becomes this. The difference, the pressure differential, I believe is what it's called, times the exit surface area of the nozzle. And so hopefully you can see how I did that substitution there. It's pretty neat how the mathematics all works out in this, but it does. Alright, so in this video we learned that the fuel and oxidizer combination, as well as the nozzle area, shape, and the throat of the nozzle determine what the exit velocity is going to be, and those are all components of the thrust that will be generated by the rocket engine. So I hope you guys liked the video. Make sure to subscribe to my channel and click the notification bell if you want to be notified when I release more videos in the future. Thank you all for tuning in, and I'll see you next time.